In this video, I'm going to run through topic 5, which is forces of the AQA GCSE specification. I hope you find it useful. Topic 5 starts with the distinction between scalar and vector quantities. Scalar quantities have magnitude or size only. Examples of those include speed and distance because they both only have a magnitude, which is size or a numerical value. Vector quantities have a magnitude and an associated direction. Examples of vector quantities include velocity, displacement, force and acceleration. And all of those values, it's important to remember that they have a magnitude but also an associated direction, and we need to work out which direction they are acting in. As seen on the previous slide, forces are vector quantities. Now forces can be broken down into contact and non-contact forces, which we're going to look at in a bit more detail on this slide. A force is a push or a pull that acts on an object due to the interaction with another object. So forces come around because of interactions between objects. So all forces between objects are either contact forces, where the objects are physically touching, so that happens with air resistance, so the object is actually hitting the air particles that provide the air resistance, or friction, that occurs when two surfaces slide past one another, or the normal contact force, which happens when you rest something on a table or on any other surface, or tension, which is where the force in the rope are providing the tension. They can be contact forces or they could be non-contact forces. That's when the force on the objects can occur when the object is physically separated. So non-contact force examples are such as gravitational force. So for example, a mass doesn't actually need to be touching another body for them to be attracted together through gravity. And you would notice that if you jumped off the Earth, you jump up in the air, you're no longer touching the Earth, but the force of gravity from the Earth is still acting on you. Electrostatic force, that's when you bring two charges together. Okay, again, the charges don't actually need to be physically touching before they repel one another. And finally, the magnetic force, if you bring a magnetic material into the field around a magnet, it doesn't actually need to physically touch the magnetic material for the magnet to attract that material. So those are examples of non-contact forces. Most of our understanding about motion comes from Newton's laws of motion. Now Newton made 3 laws of motion that we need to look at in a bit more detail. So Newton's first law states an object will remain at rest, which means stationary or not moving, or at a constant velocity unless an external force acts upon the object. So the first part, the idea that an object will remain at rest, is quite straightforward. You know, if something is not moving, you obviously need a force to get it going. Okay, so force needs to apply to that to make it accelerate in one direction. If the object is going at a constant velocity, though, I think some students find that more difficult to get their heads round. And the reason for that is that on Earth, if we push something, it will usually slow down, and the reason it slows down on Earth is because we've got friction. And friction is a force that's causing that object to slow down. However, if you're in space and you sense something moving at constant velocity, it will continue to move at that velocity that you set it off with for a very, very long time, and would only slow down if it came into contact with another force that was provided by a planet or something else. Newton's second law of motion is best known as an equation, and that equation is that force is equal to mass times acceleration. We use the symbols F for force, M for mass, and A for acceleration. You need to know that force is measured in newtons, which are named after Sir Isaac Newton, whose all these laws are named after as well. And he defined the Newton as the force required to accelerate an object of 1 kilogram by 1 meters per second squared. And that's the reason why we use kilograms as the units for mass in all physics calculations. Acceleration is measured in meters per second squared. Newton's third law is that every action force produces a reaction force that is equal in size but opposite in direction to the action force. Now both these forces, the action force and the reaction force, act on different objects. But any interaction between objects, the action force is applied. So for example, if I go up to a wall and push on the wall, I provide an action force to the wall. So my force is acting from me onto the wall. But the wall would push back on me with the same size force, so same magnitude, but it would act in the opposite direction. We can simplify the number of forces acting on a system by calculating the resultant force. So as you can see here, a number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together. And we call this the resultant force. So if you look at the example we've got here, we've got 100 newtons of the driving force of the car, pulling it forwards. We've got 25 newtons for the air resistance. And we've got 2 sets of 10 newtons where the wheels are in contact with the ground. That means that those forces, we could do 100, take away 25, 10 and 10. So overall we've got 45 newtons, which is 10 plus 10 plus 25 acting backwards, and 100 newtons acting forwards, which means we can replace all of those forces by a single force of 55 newtons acting forwards. So you can see now that we replace those forces with 55 newtons, and that's the force we need to consider about what's going to happen to that vehicle. Now, because we've got 55 newtons acting forwards, that means that that car is going to accelerate in the forwards direction. The next thing that we need to think about is what happens to an object if it has a resultant force acting on it. So if an object is moving and there is a resultant force, like in our case above, the object will speed up if the resultant force acting forwards. It will slow down if the resultant force is acting in the opposite direction to what the object is moving in, or it would change direction. If the object was stationary to begin with, then it would begin to move. If there's no resultant force though, when an object's moving, it will continue to move at constant velocity, and if an object's stationary, the object will remain stationary. Now, in some cases in physics, you'll be given the resultant force, but it sometimes makes more sense to try and resolve it into components. So you can see here that we've got a force of 5 newtons, which is acting at 30 degrees to the horizontal. And this force can be expressed as two forces, one that acts vertically, so which is going to act upwards, and one that's acting horizontally, which is obviously acting on the side. In order to break something into its vertical and horizontal components, there's two methods. In this, first of all, we're going to look at the first method that's available to us, which is scale drawing. So in this method, what you need to do is you need to draw the force using a protractor and a ruler. Make sure you note that your scale, for example, 1 centimetre, 1 newton. So if I wanted to use that scale, I would make this line 5 centimetres, where each centimetre represents 1 newton. So 5 centimetres means I've got 5 newtons overall. You would then draw two lines, so I've got the horizontal component here and the vertical component there. I would match them up and draw them on, and then I will be able to measure the sides of my horizontal and my vertical component using a ruler, and I'll be able to convert that into a force using the scale that I've got here. So here's a worked example for you. If I use a scale of 2 centimetres equal to 1 newton, I can work out what these values would be. So if I drew that onto a piece of paper, I would have a 10 centimetre line here first, because I've done 2 times 5, because I've got 5 newtons, but that means that each newton is 2 centimetres, so 2 times 5 gives me 10 centimetres. So I draw a 5 newton line to be 10 centimetres, and I measure the angle from the horizontal using a protractor. I would then draw on the horizontal and vertical components, and I'll be able to measure these lines. So if I measure the vertical component, which is this one here, I would notice that that would be 5 centimetres. So the newtons, the number of newtons I've got, will be 5 divided by 2, because each 2 centimetres is equal to 1 newton. And that will give me 2.5 newtons. I'll then be able to measure the horizontal component of 8.6 centimetres for this case here, and then I'll be able to convert it into newtons by dividing by 2 again to get 4.3 newtons. And if you've got a piece of paper with you and a ruler and protractor, it might be worth to have a go at this example here, because they're the values you should be able to get. The next method we're going to look at is the second method, which is going to be using trigonometry. So what I need to do first of all is identify the correct sides as opposite, adjacent and hypotenuse. So you can see here that the side that's opposite the angle, so the angle's here, the one opposite the angle is the opposite. The one that's in line with the angle is the adjacent, and the one that's the correct one between the two, that's in between adjacent and opposite, is the hypotenuse. Then I can use this trigonometry function to work these out. So I've got sine theta is opposite over hypotenuse, and cos theta is adjacent over hypotenuse. I've got that from maths, which you should know, or using the usual way you do that is SOHCAHTOA, isn't it? And then I essentially just need to put the numbers into those equations. So you can see for sine theta, my sine angle's 30, so I can substitute that into there. And I'm trying to find out the opposite, so I don't need to put that in yet. But my hypotenuse is 5, so I've got sine theta equals my opposite, which I'm trying to find out, over 5. So 5 times sine theta will give me my opposite value, and therefore 2.5 newtons is the value of my vertical component, which is the same value we got when we used the scale drawing. To work out the horizontal component, I'd use cos theta is equal to adjacent over hypotenuse, and put the numbers in again, so you can see the 30 going in for the angle and the 5 going in for the hypotenuse. And I'm going to then rearrange that equation to get 5 times cos 30 is equal to my adjacent. so my adjacent is going to equal 4.3, and A is 4.3 newtons, which again is the same value we've got through the scale drawing. In terms of which method you want to use, it depends which suits you best. If you're very good at maths, then the trigonometry method probably works well for you. It is worth pointing out, though, that you can pick up more marks using the scale drawing in case you make a mistake using the trigonometry. So if you were to use trigonometry and made a mistake, you're likely to lose quite a few marks. Whereas if you did the scale drawings and made a small mistake, or didn't quite measure the angle, the side length right, or convert something right, you'd be able to pick up more marks in that method. So now let's look at the difference between weight and mass. Okay, so weight is the force due to gravity. So weight is a force. The force of gravity close to the Earth is due to the gravitational field around the Earth. The Earth's got a gravitational field strength of 9.8 newtons per kilogram, which will be given to you in the exam. And the weight of an object can be found using the equation where weight is equal to mass times gravitational field strength. This shows that, as you can see, that weight and mass are directly proportional to one another. So if I increase mass, I increase weight by the same factor. So if I double my mass, I double my weight. If I quadruple my mass, I quadruple my weight. You get the idea. And the constant of proportionality between weight and mass is the gravitational field strength. The key thing to remember here is that weight is measured in newtons and is a force, whereas mass is measured in kilograms. Now, the weight may be considered to act from a single point, and we call that point the centre of mass. There'll be more on that in the next slide. And weight can be measured using a calibrated spring balance, also known as a Newton meter. So one way to measure weight is to use a Newton meter. It's really important to remember that weight is measured in newtons, mass is measured in kilograms. You'll notice that this equation that we've got at the top here with weight is equal to mass times gravitational field strength looks fairly similar, or almost the same, as the equation that we looked at on a few slides ago for Newton's second law, where force is equal to mass times acceleration. So you can see here that weight is the force, because they're both measured in newtons. Mass obviously is the same in both cases, and acceleration and gravitational field strength there are very similar to one another. And that means if you were to drop an object on the Earth, it would accelerate, and it would accelerate at the same value as the gravitational field strength. So that would be 9.8 meters per second squared. And the key thing to remember with any force, when we're talking about forces here, we're talking about the resultant force. So if the forces are unbalanced, providing a resultant force, that's when an object will accelerate. So you're just going to look at the centre of mass in a bit more detail. So on the previous slide, we said that the centre of mass is the point at which we can assume that the object's weight acts. It's also the point at which we can assume that most of the mass is concentrated. It's worth noting that if you freely suspend an object, it will come to rest with its centre of mass directly below the point of suspension. So here you can see on this example, we suspended it from point A, and we've dropped what we call a plumb line down here. That's just a line that will hang freely, so straight down. And if we were to draw on this plumb line, the centre of mass would be somewhere along that line. We could then change and suspend the point from point B, and draw down a line again, and where those two lines intersect, that is the point where the centre of mass would be. We could also, just to double check, suspend it from a different point, and all three lines would then intersect the centre of mass. For symmetrical objects, the centre of mass is along the axis of symmetry, and objects, and in some cases you need to be able to remember that the centre of mass for some things like a tyre, for example, wouldn't actually be in part of the object. It would be suspended in free space in the middle of the tyre. The final thing to point out is that objects with wide base and a low centre of mass, such as this vase here, are more stable than those with a narrow base and a high centre of mass, like these champagne flutes, which means that the champagne flutes are easier to knock over than the vase. So now we're just going to briefly look at the difference between distance and displacement. Distance, remember, is how far an object moves. Distance does not involve direction and therefore is a scalar quantity. Whereas displacement includes both the distance an object moves and the direction that object is moving in. So displacement, remember, is the distance an object moves measured in a straight line from the start point to the finish point and the direction of that straight line. That makes displacement a vector. Now we can use this as an example. So if you look over here at this track, I'm going to assume that track is 2.5 meters from start to finish. Okay, and with that track, it's we're going to set these cars going from their original starting point. I'm going to go around the track and come back to where they started from. So because the track is 2.5 meters, the distance those cars will move is 2.5 meters. But the displacement the cars will have is 0 meters. And the reason it's 0 meters is they've started back in the same position that they originally came from. So that's an example where distance can be greater than displacement. We're now going to look at the difference between speed and velocity. It's worth pointing out that speed does not involve direction, which makes speed a scalar quantity, and speed is the distance travelled per unit time. You can calculate speed using the equation that's shown there: distance travelled in meters, speed measured in meters per second, and time measured in seconds. An object's speed is rarely constant and often changing. The average speed can be calculated for non-uniform motion, and this will be found by dividing the total distance by the total time, and that would give us the average speed for that distance to be travelled. The velocity of an object is different to speed because the velocity of an object is a speed in a given direction, and velocity is a vector quantity. You need to be aware of some typical speed values, and these are shown over here. So you need to know that walking typically is about 1.5 meters per second, running is typically about 3 meters per second, cycling is typically about 6 meters per second, and you also need to know these exact ones. So the speed of sound is 330 meters per second, and the speed of light in a vacuum is 300 million meters per second. Moon, for example, in this case. One example where I might ask you about the difference between speed and velocity is in circular motion. So when an object moves in a circle, they often have a constant speed, but a changing velocity, as the direction of the object is constantly changing. So you can see on this side we've got a diagram. You can see the velocity at the top is pointing in this direction. It might move at the same speed all the way around, but as it does move, as it does move around in a circle, its direction changes, and that changes velocity. So you can see here the velocity now is acting in this direction. The size of that arrow stays the same, denoting the speed, and the magnitude stays the same, but the direction changes, which means velocity is changing, and also means that the wheel is accelerating. Sometimes the examiners like to ask you about circular motion in different contexts. So you can see here we've got 3 contexts to talk through. First one is this one here, where you've got the car going around a corner. That is circular motion because it's going around in a circle, and the force is provided by the friction between the tyres and the road surface. You could also have this example where something's being swung around on a piece of string. There, the force is the tension in the string. You then got a final example through pictures here. We can see the Earth with the moon orbiting it, and the force there is gravitational force. You could also have examples such as the electrons orbiting the atom, and there what's holding them in place is the electrostatic force of attraction. Key things to take from circular motion, though, is that speed remains constant, but because the direction of the wheel is changing or the circular motion is changing, that means the velocity is changing. So now let's look at acceleration. Acceleration is a rate of change of velocity. Acceleration is measured in meters per second squared. And you can see the equation that you'll have is a is equal to v minus u over t. We're now going to look at distance time graphs, and it's key to remember that the gradient of a distance time graph is equal to the velocity. There's a few different things you need to know about distance time graphs. The first one is how to show something speeding up, and speeding up means that the line is changing. So you can see here that if the gradient is velocity, the gradient here is increasing, which means velocity is increasing. If an object is stationary, it's not moving, there will be no gradient, so it will be a straight line, as indicated there. So the distance is not increasing with time. Constant speed, you'd have a constant increase in distance with time, and you can see that gradient would be constant, which is why velocity is constant for a diagonal line like that. If something's going to slow down, you can see the gradient is decreasing on this line, so a curve in this direction would be an object slowing down. You could be expected to work out the velocity from a distance time graph by calculating the gradient, or you could also be expected to draw a distance time graph in the exam, or interpret a distance time graph that had been added up with lots of different parts. Following on from distance time graphs, we move on to velocity time graphs. So you can see these here. So for constant speed going forwards, it's a straight line above 0. Is a constant speed going forwards for a velocity time graph. A stationary object this time would have a straight line on the 0 mark. So its velocity will be 0 there, straight along the axis. If it was slowing down, we'd have a decrease in velocity. So it starts off at something like 4 and go down to 0 in that case. If it was speeding up, we'd have an increase in velocity like this one shown here. So starting at 0 and going up to something like 4. And then finally, we can also show objects moving backwards by using a line in the negative, on the negative axis as shown there. So it will be constant speed but going backwards. Key things to remember about velocity time graphs is that the gradient, if you calculate the gradient, you calculate the acceleration. but if you calculate the area under the graph, that is the distance travelled by the object. So we're going to look at this velocity time graph now. I'm just going to talk through the different sections. So you can see between 0 and 20 seconds, that object is not moving because the velocity is 0 meters per second. After 20 to 30 seconds, between 20 and 30 seconds I should say, that object is going to accelerate. It's going to go from 0 to 20 meters per second. Between 30 and 40 it travels at a constant speed, which is 20 meters per second. It will then accelerate again between 40 and 50 seconds up to a new speed of 30 meters per second, which it travels at for a further 10 seconds between 50 and 60 seconds. It will then decelerate to 0 between 60 and 90 seconds, and that's shown by this line going down here. Now to those labels, you can see them there. So you can see first of all stationary when it's 0, accelerating when we've got a diagonal line going upwards, constant velocity for a flat line or a straight line, and decelerating when the line's going down. The next part I would like to look at here is how to calculate the distance travelled by the vehicle. So if you remember from the previous slide, we said the distance travelled by the vehicle is the area under the graph. So to work out the area under the graph, what we're going to have to do is we're going to have to split this graph into different shapes so we can calculate the total area under the graph. So now split the shape up into different easy to use shapes. So you can see I'll put a line down here to make this a triangle. I'll put a line across here to make this into a rectangle. I've got another line down here to make this a triangle. We've got a rectangle there and a triangle there. And you can calculate the total area of each of those shapes and add them all together. So how you calculate them is if you use a rectangle, you're going to do base times height. If you use a triangle, you can use half base times height. So I'm going to work out the areas of each of these shapes. So we've got 1, 2, 3, 4, 5. And then once we've found the values for each of those 5 shapes, we can add them together to find the total area that is underneath the graph, and therefore the total distance that the vehicle has moved. So the first shape we're going to look at is this one here. And you can see that we've got a distance on the bottom of 10. It goes up 20 up the side. And it's a triangle, so we're going to do half times 10 times 20, and that value should give us 100. The next one we're going to look at is this, so we'll put 100 meters there, so remember. We then got this rectangle here, so you can see across, it goes 10, 20, 30. And then up the sides, it's going to go up 20 as well, so it's going to be 20 times 30, because it's a rectangle. 20 times 30, when you do that on your calculator, gives you 600, so I'll just add that one in. We're now going to run through quite a few of them together now, because you've got the idea, hopefully. So if we look at this one here, we're going to see that that one is going to be a base of 10, a height of 10 as well, going from 20 to 30, but it's a triangle, so it's going to be half times 10 times 10, which will give us 50. This one here is going to be 10 multiplied by 10, so it's a rectangle, which will give us 100. And the final one that we need to look at is this triangle here, is going across between 60 and 90, that's 30 along the base. It's going up 60 to, from 0 to 30, so it's 30 along the height, multiplied by a half. So you can now see that I've added those in. So if you look at here, again, we've done 10 across, multiplied by 10 up, divided by 2, so it's a triangle to get 50. Here we've done 10 up, multiplied by 10 across to get 100. And then here we've done 30 down, and 30 across, divided by 2 to get 450. Now total value for my total distance will be 100 plus 600 plus 50 plus 100 plus 450. So you can see at the bottom of the screen now, I added that calculation in. You can see what I've done there. 100 plus 600 plus 50 plus 100 plus 450 will give me my total distance travelled as 1,300 meters. So that is one way to work out the value of the distance travelled from a velocity time graph. Remember, it's always the area under the graph. There's some ways to do it. This one is breaking it up into shapes and working it out that way. The alternative method is by counting the number of squares. That will be a little difficult in this example because the squares aren't quite big enough, but it could be on the exam that you're asked to calculate the distance travelled from a velocity time graph by working out the area under the curve by estimating the number of squares under that graph. We're now looking at the same velocity time graph again, but this time we want to find the acceleration between different points. So he wants us to first of all find the acceleration between 20 and 30 seconds. So you can see over here this is 20 and 30 seconds, so it's accelerating there. Remember that the acceleration is calculated using the gradient. So what I need to do is gradient, remember, is a change in your y-axis divided by a change in your x-axis. So you can see here on the equation, the gradient is equal to change in y or change in x. Remember that the acceleration is a gradient of the velocity time graph. So what we need to do is we need to work out a change in y and change in x for the first one. So you can see here between 20 and 30 seconds, the change in y is 20 seconds and the change in x is 10 seconds. So if we follow that working over here for this triangle, as I said before, 10 is my x, so put 10 in there, 20 is my y, so 20 over 10 is 10 meters per second squared, so my acceleration is 10 meters per second squared in that bit. The next one it asks you for is between 40 and 50 seconds, so this one here, between 40 and 50 seconds I've got a change of 10 on the x, and also a change of 10 on the y. And you can see that it's because 50 minus 40 gives you 10, so between the 40 and 50 you've got 10 seconds of time taking place, and between 20 meters and 30 meters we've got a gain of 10 meters. So using the equation over here now, you can see you've got a change of 10 divided by 10 is equal to 1 meters per second squared. This now brings on to the final one, which is between 60 and 90. So between 60 and 90, the change in our gradient is actually a minus value because it's going down. And it's gone from 30 to 0, so that's going to be minus 30 in terms of change in y. And it's gone from 60 to 90, so that's been a change of 30 seconds on the x. You can see now we've added those values into the equation, so we've got our acceleration is equal to minus 30, that's because it's gone from 30 to 0, so 0 minus 30 is minus 30. And here we've gone from 60 to 90, so 90 minus 60 will give you 30 here, and that gives you an overall acceleration of minus 1 meters per second squared. Why is it a minus? That means it's actually slowing down, so it's decelerating in that area. So just a reminder that to calculate acceleration for velocity time graph is the gradient of the graph. And if you have a distance time graph, the gradient of that graph is velocity and can be calculated in the same way as what we've done here. So now moving on to required practical activity number 7, and this is to investigate the effect of varying the force on the acceleration object of constant mass. That could be experiment version 1. So in that case, we're going to have a constant mass, we're going to change the force acting on the object, and we're going to measure the acceleration. Investigation number 2 in this practical is to investigate the effect of varying the mass of an object on the acceleration produced by a constant force. So the key principles involved in this practical, the first one we're going to look at is the idea of using a friction compensated slope. So friction compensated slope is actually shown in the diagram, and what we've done here is we've raised the slope slightly off the ground. And we've raised it to the point at which the trolley won't begin moving by itself, but it will still, once it's pushed, it will not be stopped by friction. So the reason we use a friction compensated slope, and that's been done by tilting the runway, is because if we didn't do that, the measured force would be greater than the resultant force. And the reason for that is that the resultant force, the measured force, would have to overcome friction as well as being the resultant force that we're applying. So we've compensated for friction by increasing the angle at which we've raised the slope. The second key principle is the use of light gates. So you can see we've got a light gate here and a light gate there. And what light gates allow us to do is allow us to measure time to a higher resolution. Okay. They also allow us to use data loggers on a computer that will help assist us with our results. So the idea is we will probably set those light gates to measure the velocity of the trolley as it passes through this stage and the velocity of the trolley as it passes through this stage. It will be connected to some data software that will allow us then to measure the time between the two light gates. Remember, light gates have a small laser running between the 2 points, and they're broken when the trolley passes through that. Now, if we manage to measure time as well as the initial velocity and the final velocity, we'll be able to calculate acceleration using this equation here. Because acceleration is the final velocity minus the initial velocity divided by time, and that will allow us to calculate acceleration. Alternatively, we'll be able to measure the distance between the two light gates and then use this equation here, which is given to us on the equation sheet. We don't need to learn this one, and that's that the final velocity squared minus the initial velocity squared is equal to 2 multiplied by acceleration multiplied by displacement. We could rearrange that to get A is equal to V squared minus G squared over 2S, and that would allow us then to calculate acceleration from those values. In the first part of the investigation, remember I told you there's 2 parts to the investigation here. The first one, remember, is that we're going to vary force and see the effect on acceleration for constant mass. So in that case, how we're going to change force is by using W equals m times g. So we're going to add more masses on here, more masses onto that mass hanger, and that's going to cause that to pull down with a greater weight. So there's going to be more weights pulling this down. So you know our force is W acting down in this direction. Now it's really important here that whenever we take a mass off this value, off here, we need to add it to our trolley. Or we could remove a mass from the trolley to add to the mass hanging. So the mass of the system, the whole system stays the same. The alternative way is to change the mass and keep the force constant. So we'd have the same force pulling the trolley down in this direction. We could add more masses to our trolley for the second experiment. And you should be able to talk the experiment through and also point out the key things principles that I've gone through here as well. Okay, we're going to look at stopping distance now. So stopping distance is equal to thinking distance plus braking distance. So stopping distance, the definition is the sum of the thinking distance and the braking distance. Thinking distance is the distance travelled during the driver's reaction time. Remember, the key thing with all of these are always distances. So you've got to say it's the distance travelled during the driver's reaction time. Okay, the driver's reaction time, you should know, is typically 0.2 to 0.9 seconds. Obviously, it increases if we're under the influence of alcohol or if we've been using drugs or something like that. The braking distance is the distance the vehicle travels under the braking force. So once the brakes have been applied. But your overall stopping distance is the combination of those two together. So thinking distance plus braking distance equals stopping distance. Okay, so now we're going to look at facts that increase stopping distance. So remember, stopping distance is made up of thinking distance and braking distance. There are some factors that will affect both thinking and braking distance, and some that will affect just one of them. So if we look at thinking distance, if you have a greater velocity, the thinking distance is going to be greater. If you've got distractions, such as using mobile phones, if you're tired, or if you're under the influence of alcohol and drugs, all of the thinking distance will increase for all of those things. So the greater velocity also affects braking distance. The faster you're travelling, that impacts both thinking and braking distance, and therefore will increase your stopping distance by a greater effect. The factors that affect braking distance exclusively, so that only affect braking distance and don't affect thinking distance, are the following. So road conditions, so if it's wet or icy, it's going to take you longer to stop. If you've got bald tyres, so you've not got any grip on your tyres, it's going to take you a longer distance to stop. If your brakes are worn, they won't be working as effectively, so it'll take you a longer distance to stop. And also, if you've got more passengers in the vehicle, making it heavier, that will also take you a longer distance to stop. The next thing we need to look at is what actually happens when you apply the brakes. So when a force is applied to the brakes of a vehicle, work is done by the friction force between the brakes and the wheel. That reduces the kinetic energy of the vehicle, and the temperature of the brakes will increase. The greater the speed of a vehicle, the greater the braking force is needed to stop the vehicle in a certain distance. The greater the braking force, the greater the deceleration of the vehicle, and large decelerations may lead to brakes overheating and or loss of control. So now let's look at terminal velocity. Terminal velocity is the maximum speed that an object can reach, and that will occur when the forces on that object are balanced. So we look at the example of a skydiver. So originally, when you first jump out of a plane as a skydiver, there's no force acting on you other than your weight. So the instant you jump out, you're not moving through the air, so you're not colliding with air particles. So there's no air resistance, it's just your weight pulling you down. As you begin to speed up as you fall down due to weight, you've got a resultant force acting downwards, that's going to accelerate you down, which means you're going to get faster. As you get faster, you're going to collide with more air particles, which means your air resistance is going to increase. So you can see here, we're having an increase in the air resistance because we're colliding with more particles in a given time. Eventually, the air resistance will increase to the point at which it's the same size as the weight force acting down. That means there will be no resultant force acting on the skydiver at this point, which means you will no longer accelerate, and therefore he's met a constant velocity, and that is his terminal velocity. That's the fastest speed he can travel at. So now, obviously the skydiver doesn't want to hit the ground travelling at that speed because he's going to hurt rather a lot. So he needs to slow himself down, and how he does that is by opening his parachute. The parachute has a large surface area, which means it collects more air particles and collides with more air particles in a given time, which increases the air resistance. So as air resistance increases, the skydiver will have a resultant force acting upwards. That will cause the skydiver to slow down. As he slows down, he'll have less collisions with the air particles in a given time, and so will his parachute, which means that the air resistance will decrease because there's now less collisions. Eventually, the air resistance will decrease to the point at which it equals weight again, and the skydiver will now be moving at a new constant velocity, which is his terminal velocity whilst using a parachute. Because these two are balanced, that means there's no resultant force, and he's travelling at constant velocity, which is much lower when he's got his parachute open than it would be without. If we plotted the journey of a skydiver on a velocity time graph, this is what it would look like. So at first we've got a large acceleration because his weight force is so much greater than his air resistance. His acceleration begins to decrease as he travels faster, and the reason for that is that air resistance is increasing. So his acceleration, he will continue to accelerate until point C. At point C, he's going at a constant velocity. This is where the two forces, weight and air resistance, are balanced. What happens here is the skydiver will now open his parachute and he'll begin to slow down, which you can see in this line here along D. Eventually, as he slows down, the reason he's slowing down, remember, is that the air resistance is now greater. But as the air resistance is greater, that causes a larger force due to air resistance. So it slows him down, which means that he collides with less particles in a given time, which reduces his air resistance until the point when air resistance equals his weight again at point E, and he's now moving at the lower terminal velocity. Terminal velocity, remember, occurs when there is no resultant force, and weight and air resistance are equal to one another. When a force causes an object to move through a distance, work is done on that object. We can work out the amount of work done in moving an object using the equation, which is work done is equal to force times distance moved in the direction of that force. Please remember that we're using distance as an S, and this is an equation that you do need to learn. Work done is almost like a measure of energy transfer, so we measure that in joules, and where 1 joule is equal to 1 Newton metre. If work is done against frictional forces acting on an object, then there will be an increase in temperature for that object. When work is done to a system, energy is transferred to the system, so the energy stored of that system increases. When work is done by a system, the system energy is transferred away from the system, so the energy stored of the system will decrease. Remember that work done is essentially transfer of energy. We now find ourselves looking at force and elasticity. So you need to know when you're looking at force and elasticity, we're looking at bending and stretching objects or change the shape of them. Whenever you try and change the shape of an object, so either stretch it or compress it or bend it, you need to apply two forces. One to fix the object in place, and then one to do the stretching or bending. The extension of an elastic object is directly proportional to the force applied, provided the limit of proportionality is not exceeded. What we mean by that is that you don't go beyond and stretch the elastic object too far, because then it will become deformed. Remember that directly proportional means that if you increase one thing by a factor of 2, for example, the other object would increase by a factor of 2. So if we doubled the force in this case, extension would also double. And the constant of proportionality between the two things here is called the spring constant. So you can calculate calculations involving an extension by using the equation you can see here, which is force is equal to spring constant times extension. The next thing to point out is the extension is the extended length minus the original length. So it's always important to measure the length, the original length of the object you're stretching first, and then the extension will be the extended length, whatever you extend it to, minus the original length that you've measured in the first place. This also applies to compressions, where E in this case, instead of being the extension, will be the compression of the object instead. Following on from this, elastic potential energy is the energy stored in a system when work is done to change its shape, so long as the system can return to its original shape again. A force that stretches or compresses a spring does work, and elastic potential energy is stored in the spring. Provided the spring is not elastically deformed, the work done on the spring and the elastic potential energy stored are equal. So this could be one of those equations that you're asked to combine. So work done is force times distance, would maybe give you your elastic potential energy, and you might be expected to work out E, for example, using this equation here. This equation you don't need to learn, this one's given on the equation sheet, and that's elastic potential energy is equal to 1/2 times spring constant times the extension squared. This is a quite common one to come up for multi-step calculations, because you could be expected to find K using F equals K times E, or you could be expected to work out the elastic potential energy from, as we've already discussed, the work done. Okay, so we can continue with extension now for our required practical activity number 6, and in this practical activity you're asked to investigate the relationship between force and extension for a spring. We're just going to run through the method that how you could do this. So you can see the diagram over here. You've got the clamp stand and the spring and the mass, and basically you hang a spring from the clamp and secure it so it does not come off. You want to clamp, ideally you want to clamp here to make sure your clamp was clamped on using a G-clamp, and you attach this to the clamp here and make sure it's nice and tight. You're going to hold a ruler vertically. Now to do this, you should ideally use a set square like this example here. So you've got your ruler vertically here, and you're reading off from your set square along that bit, and that's going to give you your value that you need for your spring length. Okay, you measure the original length of the spring as we discussed earlier, and you're going to subtract this from all of the values. You then hang the mass hanger on, and once you've hung the mass hanger on the spring, you're going to then measure the spring length again. You record the extended length and the mass that you've used, and then you're going to calculate the extension of the spring by using the equation extension equals extended length minus the original length. You repeat this process for multiple masses, and then you're going to plot a graph as we've done over here, which you're going to see extension versus stretching force, or force applied. Once you've done that, you can calculate your gradient, and your gradient of this result will give you your spring constant. If you get a graph here, notice this curve point here, that's when the elastic limit has been reached, and the graph is starting to curve because it's exceeded the limit of proportionality, and that spring is likely to be deformed from there on in. The final thing I just want to say on this practical is the reason we're using the set square is to avoid parallax errors, and that's one way that we improve the experiment and the quality of our data. Like with any experiment, you can also repeat your results to make sure that your results are accurate. And this removes random errors. Finally, we're going to look at momentum. So any object that has both mass and velocity has a momentum. And momentum can be calculated by using the equation momentum equals mass times velocity. You are expected to know this. Momentum has the units which are nice and straightforward to use, which is kilograms, meters per second. And the reason it's those is because mass is measured in kilograms and velocity is measured in meters per second. So you multiply those two things together, you get kilograms meters per second. The final thing you need to be aware of for momentum is the conservation of momentum states that in any collision or explosion, momentum is conserved, which means the total momentum before a collision is the same as the total momentum after a collision, as long as no external forces act upon that system. So it could be that you're given an example such as a collision, you need to work out a total momentum before by finding the momentum of each of the individual objects involved in that collision, and then you'll be able to work out the total momentum afterwards because it's the same as the total momentum before. Okay, that brings us to the end of the the content that's on the combined papers. From here on in, we're only going to look at triple papers, so if you're doing the combined GCSE, you can stop watching the video now, and I really hope you found it useful. If you're doing the triple GCSE, I'm afraid you've got a few more slides, so please just keep watching. So to follow from what we were doing previously, we're going to look at change in momentum. So when a force acts on an object that is moving or is able to move, then a change in momentum occurs. We can derive the equation for this as follows. So I've done a derivation here. So we start off with the equation from Newton's second law, which is force is mass times acceleration. But we also know that acceleration is the change in velocity over time. If we substitute these in here, you can see that I've tried to highlight it in reds. So F equals m times a. For the a, I'm going to substitute this bit in. So I'm going to write force is equal to mass times the final velocity minus the initial velocity over time. So we get this expression now when I combine it together. F equals m multiplied by v minus u over t. So v minus u, remember, can be exchanged for the change in velocity, the delta v sign. So F equals m delta v over t. You should know that from the previous slide that we just looked at, the momentum is equal to mass times velocity, which is this bit here. So we can see that F is equal to m delta v over t, which means that F is equal to momentum, or change in momentum over time. Now this is really important. So force is equal to change in momentum over time. So you can see there that whenever a force is applied, we are changing the momentum of an object in that time frame. But this is really important for safety features. So safety features all aim to reduce the force acting on a person for a given change in momentum. So it doesn't matter what the collision you're in, your change in momentum is going to be the same. You're going to be going from whatever speed you were travelling to zero probably. And in what we want to do is we want to make sure that the people involved in those collisions are safe. And how we do that, we want to decrease the force. So the change in momentum for crash is the same. The force can be reduced by making the time of the impact last longer. So you can see here from this equation, if we increase time, we're going to decrease force. Because if this gets bigger, we're going to be dividing the same number by a larger value, which makes that smaller. So this is how airbags work. Airbags increase the time taken for the collision, therefore reducing the force on the person. Seatbelts, again, do the same thing. They increase the time of the collision and reduce the force on the person, and so do cycle helmets and crumple zones. They all work in the same way. We now move on to look at moments. A force or a system of forces may cause an object to rotate, and the turning effect of a force is called the moment of the force. The size of the moment can be found by using the equation below, which is the moment of a force is equal to force multiplied by the perpendicular distance from the pivot. Here we use the equation m for moment, f for force, and d for perpendicular distance. You notice that the moments of a system are balanced when the total clockwise moment about a pivot is equal to the total anti-clockwise moment about that pivot. So we look at our example here where we've got the pivot in the centre. We can see that our clockwise moment, this one here, because it's turned clockwise, is equal to 20 newtons multiplied by the perpendicular distance, which is 1 metre, to get 20 newton metres. That is balanced out by the anti-clockwise moment, which causes it to rotate anti-clockwise, 10 newtons, if that's moved to 2 metres from the pivot, because 10 times 2 also gives us 20 newton metres. You also need to be aware that lever and gear systems can be used to transmit the rotational effects of forces. So you can see in this example we've got a rotational effect of forces. We can balance out a much larger mass with a smaller mass if we move that a greater distance away, and those rotational effects can be used in levers and gear systems. Here we have an example question for moments. It says on a seesaw, Mary who's got a weight of 600 newtons balances John with a weight of 200 newtons when she sits 1.5 metres away from the pivot. How far from the pivot is John? So basically what we're going to do here is we're going to apply the principle of moments. So Mary's going anti-clockwise, whereas John's going clockwise. So the anti-clockwise moment is balancing the clockwise moment. So Mary's weight, because she's the anti-clockwise side, multiplied by distance is equal to John's weight multiplied by his distance. So substituting those numbers in, we get 600 newtons multiplied by 1.5 metres is equal to 200 newtons multiplied by the distance we're after. And that gives us 900 is equal to 200 times the distance. So 900 divided by 200 is equal to our distance that we're trying to calculate. And finally we can work out that John is 4.5 metres away from the pivot. When we look at levers, a lever can be used as a force multiplier. We can see here that by having a person further away from the pivot than the load they're trying to lift, they would actually require a smaller force in order to lift that load. Now I'm going to look at pressure. So pressure is caused in fluids, and a fluid can either be a liquid or a gas. The pressure in fluids causes a force normal, which means at right angles, to any surface. And we can calculate that pressure by using the equation below, which is pressure is equal to the force normal to a surface divided by the area of that surface. We use lowercase p for pressure, capital F for force, and a capital A for the area of that surface. So pressure P can be measured in pascals or newtons per metre squared. Force is measured in newtons, and area is measured in metres squared. You also need to be aware of atmospheric pressure. The atmosphere is a thin layer of air around the Earth. It's very thin relative to the size of the Earth as a whole. Air molecules colliding with a surface create atmospheric pressure, and the number of air molecules, that's the weight of air, above a surface decreases as the height of the surface above ground level increases. So basically, as height increases, there is always less air above a surface than at a lower height, and therefore increasing the height causes the atmospheric pressure to decrease. We're now moving on to the final slide, so thank you for listening so far. We're going to look at pressures in a liquid now. The pressure due to a column of liquid can be calculated using the equation, which is below. This is one of the equations that's given to you on the equation sheet. Pressure is equal to height of the column multiplied by density of the liquid multiplied by the gravitational field strength. So if you use the symbols there, we get P is equal to H multiplied by rho for density multiplied by G. So pressure, remember, is measured in pascals. The height of the column H is measured in metres. The density rho is measured in kilograms per metre cubed. And the gravitational field strength G is measured in newtons per kilogram. Yeah, G should be given to you in any calculation you do, but remember, as we've said before in the video, G is roughly equal to 9.8 newtons per kilogram. You also need to be aware that the pressure in a liquid increases with increasing liquid depth, and a liquid flows until the pressure along the same horizontal level is constant. The greater the density of a liquid, the greater the pressure of the liquid. And finally, any objects that are partially or totally submerged experience a greater pressure on the bottom surface, and this pressure causes a force we call upthrust. That brings us to the end of this video. I hope you find it really useful, and I hope it helps you prepare for your exams, and the best of luck in those in the future. Thank you for listening. Goodbye.